Okay. So what if we have the improper situation happening at a point in an interval that I'm looking at the function on? Okay. So let me just kind of go right here and we'll look at this. If f is continuous on the interval from a to b, what do you notice about the way that notation works right there? Like look at that interval from a to b. What do you notice about that, the way I've written that? Yeah, that's right. So b is not included. So there's like a problem at b itself. Then what you have to do is get away from get away from that upper endpoint a little bit, right? We kind of talked about this last time. So I would take the limit as c goes to b from which side? The left, so that I can then have something where the function is continuous on the whole interval from a to c, yeah? And then I let c go to b from the left. And I do a similar thing if I have a problem at the lower endpoint, yes? We did both of those in the example that we started with last time, right? There we had a problem right in the middle of the interval, and we split it up, and then we took one-sided limits. Remember that? Okay. Here I'm just saying I'm looking at one of the endpoints being bad. Okay. If f is continuous on the closed interval from a to b except for some infinite discontinuity at c, then you split it up the way that we did, and you take the limits as you get closer and closer and closer from either the left or the right to that thing. If any one of those integrals diverges or goes to infinity, if it goes to plus or minus infinity, or the limit doesn't exist, we say that the overall integral diverges. If any part of it does, the minute you have some part of it going to infinity or negative infinity or limit not existing, you say divergent, okay? And convergent means the limits exist or are finite, and you say it would converge to whatever number you happen to get, okay? All right, let's do an example here, okay? All right, here we go. What about this? Let's do the integral from 0 to e of logarithm of x dx. Okay. Do you guys remember what the antiderivative of logarithm of x was? What did you have to use to actually compute it? Do you recall? It was in the second section of chapter 8. Integration by parts. We did integration by parts, and we got that this thing was x logarithm of x minus x plus a constant. I don't know if you remember that or not, but if you did integration by parts, that's what you would discover. That's where we did the weird thing where like u was logarithm of x and dv was like just dx. Remember that? And then we basically use integration by parts to get this thing. Now, let me ask you a question. What is the problem? What's the problem with this function on the interval from 0 to e? Yes, sir. Andrew. Yeah, that's right. Yeah. So what are you going to do? What are we going to do? It's undefined at 0. The logarithm function is, so what are we going to do? Yeah, so maybe like say limit as what? Help me out here. Yeah, a goes to 0 from the right. The integral from a to e. And now we're a little bit removed from 0. Yes, we're to the right of 0. That's nice. Yeah. And this is logarithm of x dx. And now like we have no issue with plugging a in to the function logarithm of x now, but we need to find the antiderivative first. Right, so this is going to be the limit as a goes to 0 from the right. What's the antiderivative of logarithm of x? X log x minus x. And this thing is being evaluated between a and e. Okay, interesting. Okay, so this is going to be the limit as a goes to 0 from the right of, okay, so this is a little gut check here. All right, so if I plug e in for x, it's going to be e logarithm of e. E logarithm of e. Okay, minus e minus, okay, minus this thing with a plugged in. So it's going to be minus a logarithm of a plus a. You see what I'm saying here? Yeah? Okay. Now, what about the a logarithm of, what about the e logarithm of e thing? What's that? Yeah, because what's logarithm of e? 1. And so this part just ends up being 0. Interesting. Okay. Logarithm of e is 1 because it's logarithm of e to the 1, right? All right, so let's see. It's going to be the limit as a goes to 0 from the right of a minus a logarithm of a. Huh. Okay. Okay, the a part is pretty straightforward. You know what I'm saying? What about the a logarithm of a part? What do you think about that? What's the form of that thing? What does logarithm go to as a goes to 0 from the right? Do you remember what the graph of logarithm looks like? Yeah, here's what the graph of logarithm looks like. It goes like this. Remember this? Like that? That's what y equal to logarithm of x looks like. Okay? This right here is 1. Okay? So if a goes to 0 from the right, you can see that the logarithm function is plunging to minus infinity, right? So what is the form of this thing right here? A logarithm of a, it's like, yeah, it's like 0 times, technically speaking, it's like 0 times negative infinity, but I mean, who cares about pluses and minuses here? It's still 0 times infinity. Know what I mean? And what do we call those kinds of limits? We had a term for that. Indeterminate. Yeah, this is an indeterminate form. And we hope that L'Hopital's rule is something that might help us in such a situation, right? Is there a way to let L'Hopital help us out here a little bit? Maybe. Okay. Yeah. All right. So keep talking. Tell me what you're thinking. Yeah. So this is limit. A goes to 0 from the right. This is a minus. Okay. So what you're saying is this is going to be logarithm of a over 1 over a. Okay. I'll write that as a to the minus 1 just to be extra cute about it. Yeah. But also to kind of help us think about what might happen next. Now, what's the form of this? What is the form of this? As a goes to 0, the top's going to minus infinity. And what's the bottom going to? Think about it. 1 over a tiny positive number is what? Right, right. So it's negative infinity over infinity. Okay. Okay. So again, you have logarithm of a over a to the minus 1. So what are you going to do with that? What do you apply? Yeah, L'Hopital's rule. Okay. So let's do that. Now let me sort of move. I'm gonna actually move some of this stuff out of the way. Just go like this. Okay. There we go. There we go. There we go. There we go. Okay, so just so that way you can kind of see it clearly. So this is going to be equal to the limit as a goes to 0 from the right of, what did we say it was? Just a minus logarithm of a over a to the minus 1. We made the observation that this guy right here is of the form minus infinity over infinity. So L'Hopital applies. Okay? So what do I get here? This is equal to limit a goes to 0 from the right of a. Okay, I'm not applying L'Hopital to that first thing. I'm applying it to the second thing. So I'm applying L'Hopital here, but I'm applying it to the second thing, not the first thing, right? So what is the derivative of logarithm of a? 1 over a. And what about a to the minus 1? Help me out here. Negative a to the minus 2. That's going to change this to a plus. Yeah? Right? And so it's going to be 1 over a squared. Yeah? Well, yeah, but I changed the negative to a positive. Does that make sense? The negative sign's canceled. Okay? But what's this? What is that? 1 over a squared. What's that? What's that in the end if I were to cancel stuff? That's just a, right? So what's this end up being in the end? It's the limit as a goes to 0 of a plus a, which is, oh, well, it's the limit of as a goes to 0 of 2a, but what does the limit end up being? 0. What? 0? That's interesting. Okay. You know what I'm saying? That's sort of interesting. But but just look at the picture for a minute. Does it make sense that the area could potentially be 0? Where's E? Isn't E maybe like over here somewhere? Okay, so here's E, right? Okay, but I'm computing the integral from not from 1 to E, but from where? 0 to E. So I'm actually also counting all this stuff over here. Okay. So essentially what has happened here, we've shown that this area is 0. So essentially what have we shown is true about the yellow stuff and the red stuff? They're the exact same area. That is cool. I think that's pretty cool. Right? So that means that this stuff here and this stuff here, that those are the same. Okay? Because this stuff right here gets counted as positive, and this stuff down here gets counted as negative. Do you know what I'm saying? Yeah? So that's interesting. Any questions on that? Yeah. No, because that's not indeterminate. Yeah, that's just there. That, I mean, we already knew what that was going to. What was A going to when A went to? That was 0. So there was nothing ambiguous about that at all. Make sense? Okay. Other questions on that? That's an interesting little exercise. Other questions on that? I wanted to back up. So like, I think it was Daniel at the end of last time that was it you, Daniel, that was saying, hey, what's the threshold for like the 1 over x to some power thing from like 1 to infinity, right? Like what's the threshold for when the thing starts to like converge to a number, okay? Let's look at that together for a minute. Okay, any questions on this before we move on to something else? Any questions? Okay. Here we go, hang on a second, clear that. So let's get out of here and I'll go over into Desmos and we'll have a peek at this together. So here's this, here we go. Look at these graphs. Okay, so I want to make sure you understand these graphs. The black graph, what's the black graph? Yeah, that's 1 over x squared. Yeah. In fact, here, I think I can do a better job than this. Let's see. What do I want the y-axis to go from? Let's go from negative, look at this, I can make this better. Negative 0.5. Actually, let's do negative 0.1. And and then go up to 1.1 or something. Okay. And let's let the x-axis go out to 50. No, that's out of control. Let's do 20 or something. Okay, or let's do 15. There we go. They all look the same actually. Let's just do 10. Okay. All right. I think we're good to go now. Okay. So here's these pictures of these graphs. What are these graphs? Well, look over here on the left. Okay, we have y equal to 1 over x squared. I'm gonna gut these things and get them out of here. Okay. So I have y equal to 1 over x squared, going from 1 to infinity. Yes. I have y equal to 1 over x, going from 1 to infinity. I have y equal to 1 over x to the 1.1, and I have y equal to 1 over x to the 0.9. Okay. 0. Okay. Which one is 1 over x? It's the blue curve. Does that make sense? And 1 over x squared, it makes sense that that graph, which is black, would be below that. The blue curve is y equal to 1 over x. It makes sense that 1 over x squared, I'm squaring numbers that are bigger than 1 in the denominator now. That thing's going to be below, the black curve is going to be below the blue curve. Why does it make sense that the red curve is below the blue curve? It's a higher power, right? And it's in the denominator, and we're putting numbers in there that are bigger than 1. Yes? Why does it make sense that the green curve would be above the blue curve? What you equal to 1? I'm actually raising it to a power less than 1. It's 0.9. Does that make sense? And that will actually make the number smaller, right? And therefore make the overall thing bigger because it's in the denominator. That's where the action is happening. Yes, sir. It was 0 times infinity. We put it, but then it's 1 over 0. What's 1 over 0? It's 1 over 0 is like infinity. Does that make sense? So it became infinity over infinity. Yeah. Yeah. There you go. If you have infinity over 0, you'd probably, that's not indeterminate. You could sort of figure out, it's going to be either plus or minus infinity, because the top's going off to infinity. The bottom is making it even bigger. You're dividing by a tiny number. Yeah. Okay. All right. So let's think about this together. So does the order of the curves make sense? Like, why is it that the green curve? Oh, and by the way, what did we discover together? I'll write it in blue just so it matches. What did we discover the integral from 1 to infinity of 1 over x dx was? What was that? That was plus infinity. Remember that? What did we figure out? Okay, for the black curve, I'll write this in black. What did we figure out the integral from 1 to infinity of 1 over x squared was? Yeah, that was 1. Huh. Now that means that the blue area under the blue curve, okay, so let's be real clear about this. The area under the blue curve which I'm trying to kind of, okay, the area under the blue curve, right? I'm trying to be real careful with how I draw this right now. Okay, that area is infinity, yes? That area is infinite, yes? But on the other hand, the area under the blue curve is not. Or the area under the black curve is not. That area is 1. Now, what do you think the area under the green curve is going to be since it's above the blue curve? Think about it. Infinity. Has to be. Just visually, it has to be. If I already had an infinite amount of area under the blue curve, then of course, the green curve is going to have infinite area as well. So I won't even compute that one. I won't even compute that one, but we'll just kind of say, just through sheer observation, that the integral from 1 to infinity of 1 over, what was that one? X to the 0.9 dx, that has to be plus infinity. If for no other reason than visually that curve is above the blue curve and hence will have more area underneath it. Yes? Okay. But there's one that's kind of interesting. So I bumped up the power on x from 1 to 1.1. That gives me the red curve. Yes? So let's think about that one together. What about the red curve? What about the integral from 1 to infinity? Let me write it as x to the negative 1.1, just to kind of get us thinking in the right direction. So what am I going to do here? Help me out. It's going to be equal to the limit as what? Limit as b goes to infinity. The integral from 1 to b, x to the negative 1.1 dx. Okay. And now what? What do you think? What is the antiderivative? Okay, so help me out here. Limit as b goes to infinity. What is the antiderivative of x to the negative 1.1? X to the negative 0.1 divided by negative 0.1. Does that make sense? But if I divide by negative 1/10, that's the same thing as multiplying by 10. Do you know what I'm saying? Dividing by 1/10 is the same as multiplying by 10. So this is like negative 10 x to the negative 0.1 evaluated between 1 and b. Okay? So far, so good? Telling you if you take the derivative of that, the negative 0.1 comes down. That will become 1 because negative 0.1 times negative 10 is just 1. And it will be x to the negative 1.1. Okay? All right. So what is the deal going to be here? Well, I'm just going to write it right here. So this is equal to the limit as b goes to infinity of negative 10 over b to the 0.1. I'm just going to write it as b to the 0.1 minus negative, which is plus 10, because I'm plugging in x equal to 1, right? So plus 10. Now I ask you, what is that limit? What does that limit end up equaling? I have b to the 0.1, and b is going to infinity, and it's in the denominator. What is the limit of that ratio going to be? What's that? 0, because it's a number over something that's getting giant. Does that make sense? The thing is being raised to the 0.1 power, but who cares? B is getting giant, and therefore if I take the 1/10 power of that thing, it's still giant. So it's like negative 10 over something giant, which is close to 0. Okay? So in the end, this is equal to what? 10. Okay? So what is the conclusion about this integral? It diverges or converges? It converges to 10. So what we would say here is the integral from 1 to infinity of 1 over x to the 1.1 dx is 10. It's bigger than the black. Does it make sense that it would be a bigger area than that which was under the black curve? Yes, it does, but it's still finite. So do you see like that there's a threshold here? It looks like the threshold is happening at a power of 1, right? And at 1, we have infinite area. And it seems like with a power smaller than 1, we continue to get infinite area. With a power bigger than 1, we're getting finite area. Make sense? Yeah, Daniel. Probably. Well, I mean, if you kind of think about it, that's probably true because remember you add 1 to the power. You're going to add 1 to the power. And so whatever you have after the decimal place is what's going to be left. Does that make sense? So yes, I think that's exactly correct. Yeah. Okay. Okay, good. Does that make sense? There's like a little threshold there at 1. That's actually going to be really important. That's one of the reasons I'm spending a little bit of time on this. That's going to be really important later on. Okay. Turns out these little 1 over x to certain power things are extremely useful when it comes to thinking about infinite sums. Okay, infinite sums. So that's kind of interesting, right? You have that blue curve, which is the threshold. That red curve is a finite area, but the blue curve is infinite area, and therefore the green curve is also an infinite area, et cetera, et cetera. So there's something really kind of mystical happening here. Yes? Maybe, but certainly for the ones that already have infinite area, it wouldn't change anything, right? For the ones that already have infinite area, you would just be adding more area and it would continue to be infinite. I have a feeling that if you went from 0 to infinity, I have a feeling that all of these would have infinite area. Didn't we do 1 over x squared from like 0 to 3? Or we did 1 over x squared before from 0 to 3, did we not? And what did we discover about that? What did we discover about it? It was infinity, wasn't it? Yeah? So I mean, look at what happens here, everyone. Here, let me change this up since we're in Desmos and we're thinking about this carefully. Man, I can't even see it. I've written all over the screen right now. Let's do y equal to 2. Okay, and then watch this. I'm going to change all of these things down to 0. Okay, 0 less than, 0 less than, 0 less than, 0 less than. Do you see what happens to all the curves at 1? Do you see what happens to them all? Before they were ordered in one way. And what happens if I go between 0 and 1? What do? They flip around into the other orders. That makes sense? So what I'm saying is, like the black curve was 1 over x squared. Now I ended up getting infinite area between 0 and 1. That's a problem. And I think the same is probably going to be true for those other ones as well. And that's a little problem I'll leave to you to kind of think about. Go over to Chuck's for lunch, play around with those, check and see if all of those don't have an infinite amount of area underneath it between 0 and infinity. Yes. If you went between 0 and 1, some of them would have finite area. But I'm saying if you went from 0 to infinity, they're all going to be infinite. If you went between 0 and 1, yes, the relationship would be flipped to where anything with a power smaller than 1 would have finite area. Anything with a power bigger than 1 would have an infinite area between 0 and 1. Yes. Yeah, there would be another threshold like that. That's a good point. Yes, sir.
So when you have 1 over x, you just need to increase x by just a little bit of power down there to have it finite.
Yeah, that's right. What that tells you is that integral from 1 to infinity, 1 over x, that thing barely diverges to infinity.
Yeah.
It
So-
barely does it. Yeah.
So could you multiply it by something at the bottom, like something like 2x or 10x, million x, whatever, and would it still be infinity, or would it,
Well, the constant isn't going to change anything because, I mean, if I multiply even by, you know, 1 over a trillion, that thing would factor out of the integral anyways, and it would still be that constant times infinity. Does that make sense? So a constant isn't going to help. It's got to happen in the power on x. Okay, that's good. Good question. You guys are asking the right kinds of questions. Okay. Other questions? Other questions? All right, that's cool. Very cool. Let me clear this. And let's look at, I think, oh, actually I'm done. Ha! I'm done, but let's do another example here. What about this? And I want you to think about this for the next 5 minutes at your table. So what about this example? Integral from, let's see, from 0 to infinity of sine of x dx. Okay? Integral from 0 to infinity of sine of x dx. And think about it before you do anything. Just sit there and think about it. Okay? But yeah, work on this with someone around you. And I'll pause this and we'll come back in a couple minutes. Okay. So let's talk through this. So what's the first thing that we do?
Yeah.
Okay, I'm gonna write equals up here, so I might give myself a little bit of room. So equals, what do I do? Limit of something. Limit as what? Yeah, limit as b goes to infinity. Integral from 0 to b sine x dx, and now limit as b goes to infinity of what's, yeah, okay. Negative cosine of x evaluated between 0 and b. And now it's going to be the limit as b goes to infinity of, okay, interesting. Negative cosine of b minus negative cosine of 0. So it's plus cosine of 0. What's cosine of 0? 1. It's 1 minus cosine of b. And you say to yourself, okay, well, what is that limit? Does that limit exist? What happens to the cosine function? It goes like this. Is that thing, it's just, cosine is just going to oscillate between -1 and 1 forever. So does this ever get close to any particular number? No. So, I mean, one thing that we would point out here is that this thing oscillates between -1 and 1, most importantly. So this thing does not exist. This limit does not exist. Okay? So what's the conclusion about this integral? Yeah, the integral diverges. And this time, can we say specifically what it diverges to? Can we say things like it diverges to infinity or negative infinity? No, it just doesn't do anything. It just, you know, it just flops around like who knows what number it's getting. It's not getting close to any particular number, yeah? And it's not even blowing up to infinity or going down to minus infinity or anything, yeah? It has like this oscillatory behavior that we cannot get a handle on, so it diverges. You just say the integral diverges and that's it, okay? All right, any questions on that? So in the last 2 minutes, I just want to point out one more example. Any questions on that? What if I did this? What if I had the integral, oops, let me clear that. What if I did the integral from minus infinity to infinity of sine x dx? Is that going to change anything? Does that change anything? Do I have to redo this problem? We already know that the integral from 0 to infinity of sine x dx does what? Diverges, okay? So that means that this integral must diverge, right? Because, look, if I break this up into negative infinity to 0 sine x dx, and I say that then it's from 0 to infinity sine x dx, like the divergence of the second integral makes the entire thing diverge. It's like the spoiled apple in the barrel, like spoils the whole bunch, right? If there's one part of the integral that diverges, everything diverges, okay? So this guy diverges. We've already seen that. Therefore, what's the conclusion? Right, so the integral diverges. We don't have to think about anything else. We're already done. There's nothing new to think about here. You could go and do the same thing down to minus infinity if you wanted, but I'm telling you, you would discover that the same thing is true, right? But it doesn't matter, even if that part was finite. If it converged to something, the second part doesn't, and so the whole thing would diverge. Okay? So that's how this works. Any questions? All right. All right, that's it.